What if I told you that right now, as you're watching this, a single particle could exist in two places at once, or that an object's fate isn't decided until you look at it? This isn't science fiction. It's the bizarre, beautiful reality of quantum mechanics, a realm where the rules of the universe as we know them twist and shatter. Think about Schrödinger's famous cat trapped in a box, simultaneously alive and dead until someone opens it. That paradox isn't just a thought experiment, it's a window into the quantum world, where possibility and reality blur in ways that challenge everything we think we understand. Quantum mysteries aren't just academic curiosities. They're the threads that could unravel the universe's deepest secrets, from the nature of time itself to the hidden fabric of space. Picture this: particles that communicate instantaneously across galaxies, realities that split like branches on a tree, or energy that appears out of nowhere. These aren't wild guesses, they're phenomena scientists are grappling with right now, clues hidden in the fine print of reality waiting to be decoded. And the strangest part, the more we learn, the less the universe makes sense. That's where this journey begins. Over the next 30 mysteries, we'll venture into the heart of quantum enigmas that defy logic but could hold the keys to existence itself. Each one is a puzzle piece in a cosmic tapestry, revealing glimpses of a reality far stranger than we ever imagined. So if you've ever stared at the night sky and wondered what's really out there, or questioned the very nature of what's possible, you're about to dive into the answers, or at least the mind-bending questions that might lead us there. Strap in, the universe is about to get a whole lot weirder. Imagine throwing a baseball and watching it suddenly ripple outward like a wave, spreading through the air before snapping back into a solid ball the moment someone tries to catch it. That's the essence of wave-particle duality, one of quantum mechanics' most head-spinning revelations. Tiny particles, electrons, photons, even entire molecules don't play by the rules we expect. They exist in this strange limbo, flickering between behaving like compact particles and spread-out waves, depending on whether we're watching them or not. The proof comes from a deceptively simple experiment. Shine light through two narrow slits and observe the pattern it creates on a screen behind them. If light were purely made of particles, you'd see two bright stripes like bullets passing through the gaps. But what actually appears is a stripy interference pattern, the kind you'd expect if light were a wave with crests and troughs overlapping. Now here's where it gets wild. When scientists set up detectors to observe which slit each photon goes through, the interference pattern vanishes. The photons suddenly act like particles again, as if they knew they were being watched. This isn't some quirk of light alone. Electrons, atoms, even molecules as large as buckaballs all exhibit the same schizophrenic behavior. It's as if reality itself hesitates, refusing to commit to one state until forced by observation. Einstein famously struggled with this, insisting the moon doesn't disappear when no one's looking. Yet experiment after experiment confirms that at the quantum scale, the moon, or at least its tiniest components, might just be doing exactly that. What does this mean for our understanding of the universe? For starters, it obliterates the classical idea of a detached, objective reality. Particles don't have definite properties until measured, suggesting that the act of observation isn't passive but participatory, shaping the world in real time. Some interpretations argue this implies countless parallel realities branching with every quantum decision, while others propose hidden variables or deeper layers of physics we haven't uncovered. But here's the kicker: wave-particle duality isn't just a laboratory oddity. It's the reason your smartphone works. Quantum tunneling, a direct consequence of particles behaving as waves, allows electrons to bypass barriers in microchips, making modern computing possible. So while it may scramble our intuition, this quantum quirk is quietly woven into the fabric of everyday technology, proving that the universe's deepest mysteries often hold its most practical keys. The moment you look at a quantum system, something extraordinary happens. The wave function collapses. All those ghostly possibilities, those overlapping states, suddenly snap into a single, concrete reality just because you measured it. This isn't a metaphor, it's the core strangeness of quantum mechanics, where observation isn't just passive watching but an active force that shapes reality. Take the double-slit experiment again. When no one's looking, particles exist as probability waves, exploring multiple paths at once. But the instant you set up a detector to see which slit they pass through, that spread out wave funnels into a single point, like fog condensing into a raindrop. This raises a dizzying question. What is observation? Does it require a conscious mind, or is any interaction with the environment enough? The Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg, takes a pragmatic view. Quantum systems remain in superposition until they interact with a macroscopic measuring device like a detector in a lab, at which point the wave function collapses into one outcome. No deep philosophy about consciousness needed, just the unavoidable disturbance caused by measurement. But others, like physicist Eugene Wigner, pushed further, suggesting that consciousness itself might play a role. In his famous thought experiment, Wigner imagined a friend observing a quantum system inside a sealed lab. From Wigner's perspective outside the lab, until he asks his friend what they saw, the entire lab, friend included, should remain in superposition. It's a radical idea that reality might not fully settle until a conscious mind acknowledges it. Then there's the many worlds interpretation, which sidesteps collapse entirely. Instead of probabilities resolving into one outcome, every possible outcome happens, just in branching parallel universes. In this view, the wave function never collapses. You simply become aware of one thread in an infinite tapestry of realities. It's a cosmic sleight of hand. The illusion of a single outcome arises because we're trapped in one branch of the quantum tree, unaware of the others. Yet for all these theories, no one knows exactly why observation has this power. Is it the intrusion of classical physics into the quantum realm, a fundamental limit to what we can perceive, or could it hint at something deeper, that reality is in some way participatory? The unsettling truth is that quantum mechanics gives us the math to predict outcomes flawlessly, but the why remains shrouded in mystery. This isn't just philosophy. Quantum encryption relies on the fact that observing a system unavoidably alters it. Any eavesdropper leaves fingerprints, and quantum computing exploits superposition, manipulating probabilities before they collapse into answers. So while we debate what observation truly means, the universe quietly enforces its rules, blurring the line between the seen and the unseen, the real and the potential. One thing's certain, in the quantum world, you're not just a spectator, you're part of the show. Einstein called it spooky action at a distance, a phenomenon so unsettling that it made him question the very foundations of quantum mechanics. Imagine two particles born from the same quantum event, spinning through space light years apart. According to the rules of entanglement, measuring one instantly determines the state of the other, no matter how vast the separation. It's as if they're bound by an invisible thread, communicating faster than the speed of light, something Einstein insisted was impossible, dismissing it as evidence that quantum theory must be incomplete. Yet decades of experiments have proven entanglement is very real. In labs around the world, scientists have separated entangled photons by hundreds of kilometers and still observed their instantaneous connection. When one photon's spin is measured as up, its partner always snaps to down, even if that decision happens a fraction of a second later. This isn't some hidden signal traveling between them. It's a fundamental defiance of classical physics' idea that nothing can influence anything else faster than light can cross the distance. Space and time seem to dissolve at the quantum level, leaving particles entwined in a way that renders the concept of distance meaningless. The implications are staggering. If entanglement holds across cosmic scales, it suggests the universe operates on a deeper layer of connectedness we can't yet perceive. Some theories propose that entangled particles aren't truly separate at all, but exist as facets of a single quantum system, no matter how far apart they drift. Others speculate that spacetime itself might emerge from a vast network of entangled quantum states, weaving the fabric of reality from these ghostly links. And here's where it gets practical. Entanglement isn't just a curiosity. It's the backbone of quantum encryption, where any attempt to intercept a message disturbs the entangled pair, alerting users to eavesdroppers. Quantum teleportation, yes, it's a real field, relies on entanglement to transmit information about a particle's state across vast distances, though not the particle itself. China's Misha satellite has already demonstrated this, beaming entangled photons between ground stations separated by over 1,200 kilometers. Yet for all its promise, entanglement still taunts us with unanswered questions. How does nature enforce this eerie synchronization? Is there some undiscovered mechanism, or does the universe simply not care about the limits we've imposed on it? One thing's certain, entanglement shatters our classical intuition, revealing a cosmos far more mysterious and interconnected than Einstein ever imagined. The spookiest part, we're only beginning to unravel what it means. How do you solve a problem that would take a classical computer longer than the age of the universe? You hand it to a quantum machine where entangled qubits can process possibilities in parallel, exploring solutions at speeds that defy conventional logic. This isn't futurism. Companies like Google and IBM have already demonstrated quantum supremacy, where their prototypes solved specific problems in minutes that would stump even the world's fastest supercomputers for millennia. The secret weapon, entanglement. Unlike classical bits stuck in rigid states of 0 or 1, qubits exploit superposition, existing as both simultaneously, and entanglement, linking their fates across the quantum landscape. Picture a maze with countless paths. A classical computer checks each route one by one, plodding through options, but entangled qubits explore every corridor at once, collapsing into the correct answer when measured. This parallelism transforms impossible tasks like cracking complex encryption or simulating molecular behavior into tractable challenges. In 2019, Google's Sycamore processor used 53 entangled qubits to perform a calculation in 200 seconds that would have taken Summit, then the world's most powerful supercomputer, 10,000 years. Yet harnessing this power is like trying to conduct an orchestra of ghosts. Qubits are fragile, their quantum states shattered by the slightest disturbance, heat, vibration, even stray electromagnetic waves. That's why quantum computers operate in frigid vacuum chambers colder than deep space, shielding qubits long enough to maintain entanglement. IBM's Eagle processor, boasting 127 qubits, and China's Zhuozhang, which manipulates photons for light-based quantum calculations, push these boundaries further. But the real race isn't just about qubit count, it's about error correction. Noise plagues quantum systems, introducing mistakes that multiply exponentially. To compensate, researchers bundle thousands of physical qubits to create a single stable, logical qubit, like reinforcing a rickety bridge with steel beams. The stakes: revolutionizing drug discovery by simulating protein folding at atomic precision, or turbocharging AI with quantum machine learning. Imagine designing fertilizers that slash global energy use by optimizing nitrogen fixation, or modeling climate change with molecular-level accuracy. Even Wall Street eyes quantum algorithms to optimize trading strategies, but alongside promise lurks peril. A mature quantum computer could shred today's encryption, rendering everything from bank transactions to state secrets vulnerable. That's why governments and corporations pour billions into this high-stakes duel, to harness entanglement's power before it disrupts the foundations of digital security. What makes quantum computing so electrifying isn't just raw speed, but its ability to reframe problems entirely. It's not a better calculator, it's a new language for the universe's hidden code. And as labs worldwide chase the dream of scalable, error-resistant machines, one truth emerges: the future won't be computed, it'll be entangled. No rulebook says reality has to make sense, and quantum mechanics proves it. Why does the simple act of measuring a particle force it to abandon its dreamlike state of multiple possibilities and snap into one concrete reality? This is the measurement problem, the glaring hole in our quantum understanding that splits physicists into warring camps, each with their own vision of how the universe truly works. Take Schrödinger's cat again. Before you open the box, quantum math describes the cat as both alive and dead, a superposition of states, but open it and you'll only ever find one outcome. The equations don't explain how or why observation triggers this collapse, they just predict the odds. It's like having a flawless recipe for baking a cake but no clue how the oven works. Enter the many worlds interpretation, a radical escape hatch. Proposed by Hugh Everett in the 1950s, it suggests the wave function never collapses at all. Instead, every possible outcome happens just in branching parallel universes. Measure an electron's spin as up here, and another version of you measures it down in a neighboring reality. There's no collapse, only endless splitting, with each universe unaware of the others. It's elegant but unnerving, an infinite multiverse where every choice, every quantum dice roll spawns new timelines. Critics call it extravagant, but supporters argue it's the purest extension of quantum math, free from fuzzy ideas about observation. Then there's pilot wave theory, a throwback to determinism. Here, particles do have definite positions from the start, guided by hidden pilot waves that orchestrate their motion. What looks like randomness is actually complexity we can't see. When you measure a particle, you're not collapsing anything, just revealing its pre-existing state. It's a comforting idea, restoring cause and effect, but it comes at a cost. The theory requires faster than light influences and undetectable waves, making it a hard sell for many. And what if consciousness itself is the key? The von Neumann-Wigner interpretation takes the bravest leap, suggesting that subjective awareness causes collapse. In this view, reality stays fluid until a conscious mind observes it, implying that the universe might not fully exist without observers. It's a philosophy as much as physics, blurring the line between mind and matter. Most scientists dismiss it as untestable, but it lingers because, well, nobody's found a better reason why measurement should matter. Here's the rub: all these interpretations predict the same experimental results. The math works, the stories we tell about it just differ. That's why the measurement problem isn't some niche debate, it's a battle for the soul of reality. Does the universe split, hide variables, or bend to consciousness? Until someone devises an experiment to kill off one of these ideas, the mystery remains wide open. And that's thrilling, because somewhere in this puzzle lies the truth about what reality really is when nobody's looking. Picture a ball rolling toward a hill. In the classical world, if it doesn't have enough energy to crest the top, it rolls back down every time. But in the quantum realm, that ball might just vanish from one side and reappear on the other, as if the hill weren't there at all. This is quantum tunneling, a bizarre trick where particles bypass barriers they seemingly shouldn't be able to cross, like ghosts walking through walls. The math behind it is just as mind-bending. Quantum particles don't behave like tiny billiard balls with fixed positions. Instead, they're smeared out in probability waves, and those waves don't stop at obstacles. They fade exponentially but never quite hit zero, meaning there's always a sliver of chance the particle could materialize on the far side of the barrier. It's less like jumping over a wall and more like borrowing energy from the universe for a split second, long enough to flicker through impossibly tight spaces. This isn't just theoretical. Without tunneling, the sun wouldn't shine. Inside stars, protons repel each other due to their positive charges, and the energy required to overcome that repulsion and fuse is far higher than what's available. Yet tunneling lets protons cheat the odds, sneaking through the barrier often enough to ignite nuclear fusion and power the cosmos. The same phenomenon fuels radioactive decay, where particles escape atomic nuclei they're supposedly trapped inside. Closer to home, tunneling is the unsung hero of modern electronics. Your smartphone's transistors rely on electrons tunneling through nanoscale barriers to switch states, enabling the lightning-fast processing we take for granted. Flash memory, that's tunneling storing your photos. Scanning tunneling microscopes, they map atoms by measuring how electrons tunnel between a probe and a surface, revealing landscapes invisible to ordinary optics. But the implications stretch beyond practicality. Tuning suggests spacetime might be more porous than we think, with particles slipping through gaps in reality's fabric. Some theories even speculate that the Big Bang could have been triggered by a quantum tunneling event, a universe burrowing into existence from nothing. Here's the wildest part: tunneling might not be limited to the quantum scale. In 2020, scientists observed molecules with thousands of atoms tunneling in experiments, blurring the line between quantum weirdness and our macroscopic world. Could larger objects even tunnel under the right conditions? The odds are astronomically slim, but the universe loves reminding us that impossibility is just a word waiting to be redefined. So next time you charge your phone or bask in sunlight, remember, you're witnessing the quiet rebellion of particles that refuse to play by the rules. The barriers we think are solid, to the quantum world, they're merely suggestions. There's a fundamental limit to how much we can know about the universe, and it's not just because our tools are imperfect. It's written into the fabric of reality itself. Werner Heisenberg's uncertainty principle lays down the law. You can't precisely measure certain pairs of properties at the same time, like a particle's position and momentum. The more sharply you pin down one, the fuzzier the other becomes. Picture trying to focus a spotlight on a dart in mid-flight. The brighter the light, the clearer you see its position, but the glare obscures its speed and direction. Dim the light to track its motion, and now its exact location blurs into shadow. That's the trade-off quantum mechanics forces upon us. This isn't a limitation of microscopes or human clumsiness. It's baked into nature's blueprint. At the quantum scale, particles don't behave like tiny billiard balls with definite trajectories. Instead, they're smeared out waves of probability, and measuring one property inevitably disturbs another. Mathematically, the uncertainty principle is ironclad. The product of a particle's position uncertainty and momentum uncertainty can never drop below a specific value, a constant involving Planck's famous number. Try to cheat it and the universe pushes back. The implications ripple far beyond physics labs. Heisenberg's principle shattered the classical dream of a clockwork universe, where perfect knowledge of the present could predict the future with absolute certainty. If you can't even measure a particle's starting conditions precisely, how can you trace its path? Determinism, the idea that every event is predetermined by prior causes, collapses under quantum uncertainty. Reality isn't a scripted play but an improv stage where particles ad-lib within strict but probabilistic rules. Philosophers have wrestled with this for decades. Does uncertainty mean nature is inherently random, or just that our knowledge is permanently incomplete? Einstein famously rejected the notion, insisting God does not play dice, but experiments keep proving the dice are indeed rolling. Even more radical is the suggestion that uncertainty might open the door for free will, not in some mystical sense, but as a consequence of nature's built-in unpredictability. If the tiniest components of reality aren't rigidly determined, perhaps larger systems, including human decisions, inherit a degree of genuine openness. Yet uncertainty isn't just a barrier, it's a feature. Without it, atoms couldn't exist, electrons orbiting a nucleus would spiral inward, radiating away energy until they crashed into the proton. Uncertainty keeps them buzzing in a stable haze, preventing matter from collapsing. It's the reason chemistry works, why materials have structure, and ultimately why life has a stage to exist on. Modern technology leans into this principle. Atomic force microscopes navigate the uncertainty trade-off to image individual atoms, while quantum cryptography exploits it to create unhackable codes. Any eavesdropper trying to measure quantum signals inevitably disturbs them, leaving a telltale trace. Even the precision of laser beams and the stability of microchips are governed by Heisenberg's math. So while the uncertainty principle might seem like a cosmic keep-out sign, it's really an invitation to rethink what knowledge means, to embrace a universe that's wilder than we imagined, and to discover new ways of working within nature's limits. The more we probe, the clearer it becomes. Reality isn't hiding its secrets. It's showing us that some questions can't be answered in the ways we once assumed. The universe, it seems, prefers to keep a few mysteries up its sleeve. Imagine flipping a coin, but instead of landing on heads or tails, it hovers in midair, spinning so fast that it's both at once until you catch it. That's quantum superposition in action, the mind-bending principle that particles don't settle on a single state until forced to by measurement. Schrödinger's cat, locked in its infamous box with a poison-triggering quantum device, embodies this perfectly, neither alive nor dead, but a ghostly blend of both until someone peers inside. While the cat scenario is a thought experiment, superposition isn't theoretical fiction. It's the daily reality of electrons, photons, and even molecules, existing in a haze of possibilities until the universe demands a decision. But here's where it gets even stranger. Superposition isn't confined to the atomic scale. In labs worldwide, scientists have coaxed objects large enough to see under a microscope, at least, into behaving like quantum schizophrenics. Take superconducting qubits, tiny loops of metal cooled to near absolute zero. When chilled enough, these don't just conduct electricity. They enter superposition, carrying current clockwise and counterclockwise simultaneously. It's as if a train circled a track in both directions at once, defying the logic of everyday experience. The real breakthrough came when researchers pushed superposition into increasingly macroscopic territory. In 2020, a team at the University of Vienna suspended glass beads hundreds of nanometers wide, still tiny to us, but gargantuan by quantum standards, in superposition states, observing them vibrate in two places at the same time. Imagine a tuning fork humming two distinct notes simultaneously, its prongs oscillating in conflicting rhythms until measured. These experiments aren't just parlor tricks, they're stress tests for quantum theory, probing where the boundary between the quantum and classical worlds truly lies, or if there even is one. Why does this matter? Because superposition is the engine behind quantum computing's potential. A classical computer processes bits sequentially, like flipping pages in a book one by one. A quantum machine, leveraging superposition, reads all the pages at once, but maintaining these delicate states is like balancing a pencil on its tip in a windstorm. The larger the object, the more easily superposition collapses from environmental noise, a phenomenon called decoherence. That's why labs battle to isolate systems in frigid, vibration-free chambers, buying precious microseconds of quantum coherence. Beyond technology, superposition forces us to confront profound questions. If particles or even molecules can occupy multiple states until observed, does reality only solidify when we look, or is there a size limit beyond which quantum weirdness fades, enforcing the classical world we know? Every experiment pushing superposition to larger scales chips away at these mysteries, revealing a universe far more fluid than our senses suggest. So next time you flip a coin, remember, at the quantum level, it's not just spinning, it's in two places at once, waiting for you to call it. The only difference, the universe hasn't decided the outcome yet. The vacuum of space isn't empty, Not even close. Quantum physics tells us it's a seething, bubbling foam of virtual particles popping in and out of existence, filling every cubic centimeter with unimaginable energy. Here's the shocker. When physicists calculate how much energy this quantum frenzy should contribute to the universe's expansion, their predictions overshoot reality by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch between theory and observation in all of science. This colossal blunder, known as the vacuum catastrophe, isn't just embarrassing. It's a flashing neon sign that we're missing something fundamental about how the universe works. At the heart of this mystery lies vacuum energy, the baseline energy of empty space itself. According to quantum field theory, fleeting particle-antiparticle pairs constantly emerge and annihilate throughout the cosmos, lending space an intrinsic energy density. The problem, when you sum up all these quantum fluctuations, the theoretical vacuum energy becomes so enormous it should have ripped space-time apart moments after the Big Bang. Yet when astronomers measure the actual expansion rate of the universe through supernova and cosmic microwave background, they find a vacuum energy density shockingly close to zero. It's like calculating the ocean should boil at 1,000,000 degrees, only to dip your toe in and find it perfectly cool. Why does this gap persist? Some theorists argue we've miscalculated how quantum fields interact across different energy scales, missing a cancellation mechanism that zeroes out most vacuum energy. Others propose entirely new physics like supersymmetry, which posits unseen partner particles that might balance the quantum books. Then there's the radical idea that multiple universes exist with different vacuum energies, and we just happen to inhabit a rare, life-friendly bubble where the numbers improbably align. The vacuum catastrophe isn't just academic. Dark energy, the mysterious force accelerating cosmic expansion, likely stems from vacuum energy's residual effects. If we cracked this puzzle, we might finally understand why the universe expands at all. Current missions like the Dark Energy Survey and future telescopes hunting primordial gravitational waves could provide clues, but for now, this remains one of physics' most glaring blind spots. Here's the humbling truth: the vacuum we call empty may hold the keys to reality's deepest secrets, if only we could hear its whispers over the deafening noise of our own theoretical confusion. Until then, the cosmos keeps its quietest enigma locked away, reminding us that sometimes nothing is everything. Black holes aren't just cosmic vacuum cleaners, they're information shredders, at least according to Stephen Hawking. In the 1970s, he made a startling prediction: black holes glow, not with light from infalling matter, but with a faint quantum shimmer now called Hawking radiation. Here's the catch: as this radiation escapes, it appears to carry away energy, causing the black hole to slowly evaporate. Poof, no more black hole. But here's where quantum mechanics throws a fit. The rules say information, the quantum states of every particle that fell in, can't truly be destroyed. Burn a book, and the ashes still hold traces of its pages. But if a black hole vanishes, taking its swallowed stars and galaxies with it, where does their information go? This is the black hole information paradox, a clash between general relativity's grim reaper and quantum mechanics' meticulous librarian. Hawking initially bet that the information was lost forever, violating a sacred quantum law called unitarity, the idea that the universe always keeps perfect track of every particle's history. This horrified physicists like Leonard Susskind, who fought to prove information survives, even if it's scrambled beyond recognition. The debate raged for decades until string theorists dropped a bombshell. What if the information isn't inside the black hole at all, but smeared across its event horizon like a cosmic hologram? The holographic principle suggests that everything falling into a black hole gets encoded in 2 dimensions on its surface, then reprojected outward as Hawking radiation. It's like burning a DVD. The 3D movie is compressed to 2D data, but if you play it back, the full picture returns. But holography isn't the only rescue attempt. Some physicists propose black holes have firewalls, searing walls of energy just inside the event horizon that vaporize incoming matter, preserving information by preventing it from ever reaching the interior. Others suggest black holes don't fully evaporate but leave behind microscopic remnants packed with the original data. Then there's the radical fuzzball theory from string theory, where black holes are tangled balls of cosmic strings, their interiors brimming with structure rather than empty voids. The stakes are higher than a theoretical squabble. If information can vanish, it undermines quantum mechanics' predictive power, the foundation of everything from chemistry to computing. Recent breakthroughs add fuel to the fire. In 2019, astronomers calculated that Hawking radiation might indeed carry information, detectable as subtle quantum fingerprints. Meanwhile, lab experiments simulating black holes with supercooled atoms or fiber optic cables hint at ways information might escape. The paradox forces us to ask, is space-time itself an illusion woven from deeper quantum threads? Do black holes hide the universe's ultimate code, or are they cosmic erasers, proof that even nature's laws have exceptions? One thing's certain, until we solve this, we're staring into the abyss, waiting for it to blink. We see galaxies spinning at impossible speeds, stars whirling so fast they should fling into the void, held together only by the grip of invisible hands. That unseen force, dark matter, the universe's most infamous ghost, it outweighs ordinary matter 5 to 1, yet refuses to interact with light or anything else we know. For decades, scientists assumed dark matter must be some exotic particle, like WIMP weakly interacting massive particles left over from the Big Bang. But after countless experiments hunting these elusive specks deep underground and in space, we've come up empty-handed. What if dark matter isn't a particle at all, but something far stranger, a quantum field stretching across the cosmos? Quantum fields are the scaffolding of reality, invisible structures that fill every inch of space, vibrating to produce particles like electrons and quarks. The Higgs field famously gives particles mass, but could there be another, hidden field responsible for dark matter? Some theories propose that quantum fields we haven't discovered yet might ripple in ways that generate dark matter's gravitational pull without emitting light. Imagine an ocean where fish, ordinary matter, swim, unaware of currents, dark matter fields surging beneath them, unseen but shaping their paths. The Large Hadron Collider is on the case, smashing protons together at near light speed, hoping to shake loose clues. If dark matter arises from a quantum field, the energy from these collisions might briefly excite it, creating detectable disturbances like tossing a pebble into a still pond and watching for ripples. Other experiments like LUX Zeppelin and the upcoming Darwin detector aim to catch dark matter particles directly, but if they fail, the field hypothesis gains traction. Here's where it gets wild. If dark matter is a quantum field, it might not be uniform. Some models suggest it could clump into exotic structures, cosmic strings, domain walls, or even bubbles where the field strength varies. These irregularities could explain why galaxies cluster in ways current theories struggle to predict. Others speculate that dark matter fields might interact weakly with ordinary matter through undiscovered forces, leaving faint imprints in particle physics experiments. The stakes crack this puzzle, and we rewrite the story of cosmic evolution. Dark fields could explain why the universe expanded as it did, or why galaxies formed when they did. They might even bridge to other mysteries like dark energy, hinting at a deeper quantum tapestry underlying everything. Until then, dark matter remains the universe's silent partner, felt but not seen, shaping the cosmos from the shadows. Einstein's general relativity paints gravity as the curvature of spacetime, a smooth, geometric dance where planets and stars bend the fabric of the cosmos. But zoom into the quantum realm, and this elegant picture shatters. Here, particles like photons and electrons don't play by spacetime's rules, they hop between probabilities, ignoring gravity entirely. This isn't just a gap in our knowledge, it's a screaming contradiction at the heart of physics. Quantum mechanics and general relativity, the twin pillars of modern science, refuse to speak the same language. The conflict erupts most violently in extreme environments, black holes where infinite density meets quantum uncertainty, or the Big Bang's first moments where the universe was smaller than an atom yet heavier than galaxies. In these arenas, relativity's equations spit out nonsensical infinities, while quantum physics shrugs. It wasn't built to handle warped spacetime. To bridge this divide, physicists have proposed theories so radical they rewrite reality's rulebook. String theory is the most famous contender. It reimagines particles not as dots but as vibrating strings, their harmonies producing every quark, photon, and graviton. The catch: these strings don't jitter in our familiar 4 dimensions, they require 10 or 11, with the extra dimensions curled up tighter than a knot. In this symphony, gravity emerges naturally, a low note in the string's vibrations. But after decades of work, string theory remains mathematically beautiful yet experimentally untested, its extra dimensions hiding just beyond our reach. Then there's loop quantum gravity, which takes the opposite approach. Instead of adding dimensions, it chops spacetime itself into tiny, indivisible loops, a pixelated universe where not even gravity can escape the quantum graininess. Picture a digital photo, zoom out and the image looks smooth, zoom in and pixels appear. Loop quantum gravity suggests reality works the same way, with spacetime woven from interconnected loops at the smallest scales. While it avoids string theory's extravagance, it struggles to explain how this quantum jumble gives rise to the smooth cosmos we see. Other ideas push the boundaries further. Causal dynamical triangulation lets spacetime build itself from geometric chunks that randomly glue together, like a cosmic Lego set assembling into order. Asymptotic safety proposes gravity's quantum version isn't infinitely strong but tames itself at high energies, like a fire that burns out before it consumes everything. And some theorists suggest gravity isn't fundamental at all. It might be an emergent phenomenon, a side effect of quantum entanglement's invisible threads stitching spacetime together. The stakes couldn't be higher. Without quantum gravity, we can't understand the birth of the universe, the core of black holes, or whether spacetime is truly continuous. Experiments like the Laser Interferometer Gravitational Wave Observatory, LIGO, hunt for clues in ripples from colliding black holes, while tabletop setups probe gravity's quantum effects on microscopic masses. Yet nature guards its secrets fiercely. What makes this quest so thrilling isn't just the promise of answers, it's the certainty that, when we finally crack quantum gravity, reality will look nothing like we imagined. The universe has always been stranger than fiction. We're just beginning to read its script. Einstein never liked the idea of spooky action at a distance. To him, quantum entanglement's instantaneous connection between particles felt like a betrayal of the orderly, local universe relativity had described where nothing could influence anything else faster than light could travel the distance. So in 1935, he teamed up with physicists Boris Podolsky and Nathan Rosen to craft a devastating thought experiment. Their goal: to prove quantum mechanics was incomplete, that hidden variables must be lurking beneath the surface, restoring classical sanity. The EPR paradox, as it came to be known, was their smoking gun. Here's how it worked. Imagine a pair of entangled particles flying apart in opposite directions. Measure one's position precisely, and you instantly know the other's position too, no matter how far apart they are. But quantum mechanics also lets you measure the first particle's momentum instead, and again, the second particle's momentum snaps into place. The paradox: in classical physics, a particle can't have perfectly defined position and momentum simultaneously, thanks to Heisenberg's uncertainty principle. So if quantum theory lets you deduce both properties of the distant particle by choosing what to measure on its partner, either the second particle somehow knows what measurement you performed light years away, spooky action, or it must have had predetermined values all along, hidden variables. Einstein bet on the latter. Reality, he insisted, shouldn't depend on what we choose to observe. For decades, this remained philosophy. Then in 1964, physicist John Bell handed science a way to test it. Bell's theorem showed that if hidden variables existed, entanglement's correlations would have strict limits. But if quantum mechanics was correct, if particles really influenced each other faster than light, those limits would be shattered. The experiments began, from Elaine Aspect's pioneering work in the 1980s to loophole-free tests in 2015. The verdict was unanimous: nature chose spookiness. Entangled particles violate Bell's inequalities, coordinating their states in ways no local hidden variable theory can explain. But here's the twist that still keeps physicists awake. These results don't just challenge locality, no faster than light influence. They challenge realism, the idea that objects have definite properties before measurement. In the quantum world, particles seem to exist in a haze of potential until observed, with entanglement stitching together a web of connections that ignore space and time. Some interpretations, like Bohmian mechanics, rescue realism by proposing a hidden quantum force guiding particles instantaneously. Others, like the many worlds interpretation, to solve the problem entirely. Every possible measurement outcome happens just in branching universes. The EPR paradox's legacy isn't just a victory for quantum theory. It's a revelation that the universe doesn't owe us intuitive explanations. Reality, it seems, is happy to play by its own rules, even if they leave Einstein's ghost scowling in the wings. Flip a perfectly balanced coin in a vacuum, and it spins in a clean, predictable arc, until air molecules start smacking into it, sending it tumbling unpredictably. That's classical decoherence in a nutshell. Now imagine that coin is a quantum particle, spinning in all possible states at once, until the slightest whisper of its surroundings forces it to choose. This is quantum decoherence, the silent killer of Schrödinger's cat, the reason we don't see bicycles or basketballs in superposition, even though fundamentally they're made of quantum stuff. At its core, decoherence is about information leakage. A quantum system left alone happily exists in multiple states, its wave function weaving a tapestry of possibilities. But the moment it brushes up against the environment, a stray photon, a passing air molecule, even a vibration in the lab bench, that interaction records information about the system, collapsing its delicate quantum dance into a single classical outcome. Think of it like trying to whisper a secret in a crowded room. Even if you don't mean to, the surrounding noise steals fragments of your message until it's no longer coherent. This isn't just philosophical housekeeping. Decoherence is the primary obstacle keeping quantum computers from revolutionizing everything. Your laptop's bits are rock solid, locked into zeros and ones by design. But a qubit, it's a skittish quantum artist painting masterpieces in multiple styles simultaneously until the outside world barges in, smearing the canvas. Current quantum processors like IBM's Eagle or Google's Sycamore must operate near absolute zero, in vacuum chambers shielded from Earth's magnetic field, just to buy qubits microseconds of coherence time. Even then, error correction chews up most of their capacity. But here's the twist: decoherence isn't just a bug, it might be the feature that builds our classical reality. Some theorists argue it solves the measurement problem by explaining why we never see superposition in everyday objects. Larger systems interact with countless environmental particles, causing their quantum weirdness to leak away almost instantly. In this view, there's no magical collapse, just entanglement spreading so wide that quantum possibilities effectively cancel each other out. A cat isn't alive and dead. It's just entangled with trillions of air molecules, photons, and dust particles, rendering its superposition undetectable. Laboratories are pushing decoherence to its limits. In 2022, a team at ETH Zurich suspended a micron-sized glass bead in a quantum superposition, then watched as collisions with individual helium atoms chipped away at its coherence. Other experiments use topological qubits, which encode information in global properties like braided quantum paths. Think of knotting a rope so tightly that local jostles can't untie it. Microsoft's Station Q bets big on this approach, though tangible hardware remains elusive. The deeper question lingers: is decoherence simply practical noise, or does it mark a fundamental boundary between quantum and classical? If we could perfectly isolate a human-scale object, would it exhibit quantum behavior? No one knows. But as quantum engineers battle decoherence to build better computers, they're unwittingly probing the origins of reality itself, one unstable qubit at a time. What if everything you see around you, the stars, the chair you're sitting on, even your own hands, is just a projection, like a cosmic hologram? This is the essence of the holographic principle, one of the most radical ideas in modern physics. It suggests that all the information in our three-dimensional universe might actually be encoded on a two-dimensional surface at its boundaries, like a movie playing on the walls of reality itself. The concept sounds like science fiction, but its roots dig deep into the mysteries of black holes and the nature of space-time. The story starts with a puzzle about black holes. When matter gets sucked into one, it vanishes from our universe, but according to quantum mechanics, information can never truly be lost. So where does it go? In the 1970s, physicist Jacob Bekenstein calculated that black holes must store information proportional to their event horizon surface area, not their volume. This was bizarre. Normally, information capacity scales with volume, like how a bigger hard drive holds more files. But black holes seem to break the rules, encoding 3D data on a 2D boundary. Stephen Hawking later confirmed this with his Hawking radiation calculations, showing that black holes slowly evaporate, leaving behind only thermal radiation, yet the information had to be preserved somehow. This led to a revolutionary idea. What if the entire universe works the same way? The holographic principle, formalized by physicists Gerard T. Hooft and Leonard Susskind in the 1990s, proposes that spacetime and everything in it might be a projection from information stored on a distant two-dimensional surface. Imagine the universe as a giant soap bubble, the physics happening inside the bubble, the motion of particles, the curvature of spacetime, could all be determined by information painted on the bubble's skin, vibrating like microscopic pixels. If true, this would mean our experience of three-dimensional space is an illusion, an emergent property of underlying quantum data. It's like watching a 3D movie in a theater. The depth feels real, but it's all just light patterns projected from a flat screen. In this cosmic cinema, gravity and quantum mechanics might finally reconcile, with entanglement acting as the threads stitching the hologram together. Experiments are already hunting for proof. Fermilab's holometer searches for holographic noise, tiny fluctuations in spacetime that would betray its pixelated nature. Meanwhile, string theorists use the principle to simplify complex problems, like modeling quark-gluon plasma, by translating it into a lower-dimensional theory. Even the debate over black hole firewalls ties back to holography. Does the event horizon itself hold the keys to decoding our universe's true structure? The implications are staggering. If reality is holographic, then time might not be fundamental, just another layer of the projection. The Big Bang could have been the moment this cosmic film started rolling. And if information truly resides at the universe's edges, then we, the observers inside, might be nothing more than shadows dancing on the walls of a deeper, stranger reality. Whether the holographic principle holds or not, one thing's certain: the universe is far weirder than it appears, and the closer we look, the more it feels like we're staring at a reflection of something we don't yet understand. Time is the silent river that carries everything in the universe, planets, people, memories forward in one unrelenting direction. or is it? Classical physics treats time as a fixed stage, an unchanging backdrop against which events unfold predictably. But quantum mechanics whispers a different story. What if time isn't fundamental at all? What if it emerges from something deeper, like the collective hum of countless quantum processes? This idea shakes the very foundation of how we understand reality, suggesting that time, as we experience it, might be nothing more than a cosmic illusion. Think of the universe like a movie. Classical physics sees time as the film strip itself, smooth and continuous, with each frame following the last in perfect order. But quantum gravity theories, like loop quantum gravity or string theory, propose something radical. Time might be more like the flicker of individual pixels on a screen, only creating the illusion of motion when you step back. In this view, time isn't woven into the fabric of reality. It's stitched together from discrete quantum events, like a mosaic made from tiny, shimmering tiles. Some of the boldest ideas come from physicists like Carlo Rovelli, who suggests time might vanish entirely at the smallest scales. Imagine zooming in on reality so far that even the concepts of before and after lose meaning. Without time, cause and effect unravel, leaving a world where events don't unfold in sequence but exist in a vast, interconnected web. It's not that time doesn't exist for us, it's that it emerges when enough quantum interactions pile up, the same way temperature emerges from the chaotic motion of molecules, even though no single atom has a temperature of its own. Experiments are beginning to probe this wild possibility. In labs around the world, scientists are studying quantum systems so small and isolated that time itself seems to blur. Take atomic clocks, the most precise timekeepers ever built. When two clocks are synchronized and then one is placed at a slightly higher elevation where gravity is weaker, they tick at different rates, proof that time is malleable, as Einstein predicted. But in extreme quantum environments like supercooled Bose-Einstein condensates, particles can enter states where traditional timekeeping breaks down entirely. Here, particles behave as if they're experiencing multiple moments at once, hinting that time's arrow might not be as rigid as we thought. The implications are staggering. If time is emergent, not fundamental, it could rewrite the story of the Big Bang. Maybe the universe didn't begin in time. Maybe time began in the universe, crystallizing from quantum chaos as the cosmos expanded. Black holes, where gravity warps time to a standstill, might be windows into a timeless reality lurking beneath our own. Even everyday experiences, why we remember the past but not the future, could be rooted in quantum statistics, the slow shuffling of probabilities that creates the illusion of a one-way flow. Yet the puzzle is far from solved. Competing theories fiercely debate whether time is an emergent property or a fundamental one. Some argue that quantum gravity must preserve time as a basic ingredient, while others see it as a casualty of a deeper, more abstract reality. The truth might lie in experiments we haven't even designed yet, hiding in the subtle interplay between quantum particles and the gravitational field. One thing is certain: if time is a quantum illusion, then our place in the universe is stranger than we ever imagined. We're not just passengers on the river of time, we're part of the current itself, shaped by processes we're only beginning to glimpse. And somewhere in the quantum fog, the true nature of time waits to be discovered, not as a backdrop, but as a story the universe tells itself, one fleeting interaction at a time. What if death isn't the end, but merely a fork in the road, a path you don't take? This unsettling possibility emerges from the many worlds interpretation of quantum mechanics, where every choice spawns parallel realities. In one version of events, you might step off a curb into oncoming traffic. In another, you hesitate just long enough to avoid catastrophe. Quantum immortality takes this idea to its logical extreme. If consciousness follows the branches where survival is possible, could you, subjectively, never experience death? The thought experiment goes like this. Imagine a modified version of Schrödinger's cat, where instead of a feline victim, you are the subject. A quantum-triggered gun is pointed at your head, rigged to fire only if a radioactive atom decays. In the many worlds framework, the atom both decays and doesn't decay, splitting reality into two branches, one where you die and another where you inexplicably survive. From your perspective, you'd always find yourself in the universe where the gun didn't fire, no matter how many times the experiment repeats. To an outside observer, your odds dwindle with each attempt, but you only experience the timelines where consciousness persists. Ethically, this idea is a minefield. If consciousness navigates toward survival, does that imply a form of narcissistic determinism, where you're the star of your own unending story? And what about suffering? A person with a terminal illness might, in some branches, endure unbearable pain indefinitely, their consciousness clinging to increasingly improbable recoveries. Critics argue this reduces the many worlds interpretation to a cosmic horror story, where death is an illusion but agony isn't, yet the implications stretch beyond philosophy. Some theorists tie quantum immortality to near-death experiences, those flashes of tunnels or loved ones reported by resuscitated patients. Could these be glimpses of branches where consciousness didn't escape? Others see parallels in quantum suicide experiments, where hypothetical observers watch a subject's survival odds vanish while the subject themselves, statistically, should always win. But here's the catch: quantum immortality isn't science. It's a speculative consequence of one interpretation of quantum mechanics, untestable by definition. You can't prove you're immortal, you can only fail to prove you're not. And that's the heart of the dilemma. When theories drift into the unobservable, they risk becoming mythology dressed in equations. Perhaps the real value of this idea isn't in its truth, but in its challenge. It forces us to confront the limits of interpretation, the nature of consciousness, and the uncomfortable fact that some quantum mysteries might forever hover beyond our grasp. After all, if the universe truly branches endlessly, there's a version of you right now reading this in a reality where none of these questions even matter. The question is, which one are you in? Place two uncharged metal plates so close together in a vacuum that there's barely room for a speck of dust between them, and something incredible happens. They're suddenly pulled toward each other by an invisible force. No magnets, no electricity, just empty space seemingly reaching out and nudging them together. This is the Casimir effect, one of quantum mechanics' most startling demonstrations that a vacuum is anything but empty. At its heart, this phenomenon hinges on zero-point energy, the idea that even in a perfect vacuum at absolute zero temperature, space thrums with quantum fluctuations. Virtual particles blink in and out of existence, borrowing energy from the universe in fleeting bursts. Normally, these fluctuations come in all wavelengths, like an orchestra playing every note simultaneously. But when plates are brought within microscopic distances, often just nanometers apart, they act like a cosmic filter. Only certain wavelengths of virtual particles can fit between the plates, while outside, all wavelengths still play freely. The result: more quantum pressure pushes inward than exists between the plates, creating a net force that pulls them together. The numbers are mind-bending. For plates spaced 1 micrometer apart, the Casimir force is roughly equal to the weight of a tiny grain of salt. But reduce that gap to 10 nanometers, about the width of 100 atoms, and the force skyrockets to the equivalent of an atmosphere of pressure. It's as if the vacuum itself becomes a vise, its grip tightening exponentially as the plates get closer. Dutch physicist Hendrik Casimir predicted this in 1948 as a theoretical curiosity, but by the late 1990s, experiments at the University of Washington and elsewhere confirmed it with stunning precision, using gold-coated plates and atomic force microscopes to measure forces as faint as a piconewton. Why does this matter beyond proving quantum weirdness? For starters, the Casimir effect is a nightmare, or a tool for nanotechnology. As engineers design microscopic machines with moving parts spaced nanometers apart, these phantom forces can cause components to stick together unpredictably. Think of it as quantum friction, an unseen hand gumming up the gears of tomorrow's tiniest devices. But researchers are flipping the script, proposing ways to harness the effect for levitation or even perpetual motion at the nanoscale. By patterning surfaces with intricate shapes like arrays of nanoscale fins or pillars, scientists have shown they can repel plates using Casimir forces, opening the door to frictionless quantum engines. Deeper still, the effect hints at zero-point energy's staggering potential. If empty space brims with this energy, could we tap it? The numbers tease the impossible. Calculate the zero-point energy in a single cubic centimeter of vacuum, and you get enough to boil all the oceans on Earth. The catch, harvesting it would require stabilizing virtual particles from their fleeting existence into something usable, a feat no one knows how to achieve. Yet the Casimir effect stands as tantalizing proof that the energy is there, lurking in the void, waiting for a paradigm shift in physics to unlock it. Some even see connections to cosmology. Could vacuum fluctuations have seeded the universe's structure, their tiny fingerprints stretching into galaxies during cosmic inflation? Or does the Casimir force hold clues to dark energy's mysterious push on the cosmos? The questions dwarf the answers, but one thing's clear. In the quiet tug between two plates, we're touching the heartbeat of empty space itself, a rhythm written in quantum static, pulsing just beneath the surface of reality. Watch a pot long enough, and it feels like it'll never boil, but what if that old saying held a grain of quantum truth? The quantum Zeno effect reveals that simply observing a system frequently enough can trap it in a frozen state, like hitting pause on reality itself. Named after the ancient Greek philosopher Zeno's paradox, where an arrow in flight is motionless at any single instant, this phenomenon shows how measurement doesn't just reveal quantum states, it actively shapes them. Here's how it works. In the quantum realm, particles don't transition smoothly between states. An unstable atom, for example, decays probabilistically. Its wave function evolves over time until collapse. But if you bombard that atom with rapid-fire measurements, checking its state again and again before it has time to evolve, you effectively reset its quantum clock. Each observation forces the system back into its initial state, like a gambler repeatedly shuffling a deck of cards before a single hand can be dealt. The result, a particle that would have decayed or changed instead remains stuck, as if time itself has stalled. Laboratories have demonstrated this with startling precision. In the 1990s, researchers at the National Institute of Standards and Technology used lasers to watch beryllium ions transitioning between energy states. By measuring the ions thousands of times per second, they suppressed the natural evolution of their quantum states, locking them in place. It's as if a flickering light bulb could be forced to stay on indefinitely just by someone staring at it relentlessly. But this isn't just a quantum parlor trick. The Zeno effect has revolutionary applications, especially in quantum computing. Qubits, the building blocks of quantum processors, are notoriously fragile, their superpositions crumbling under environmental noise. By strategically applying frequent measurements, often via carefully tuned laser pulses, engineers can artificially extend qubit coherence times, effectively shielding them from decoherence. Companies like IBM and Google already employ variations of this technique to stabilize their quantum hardware, buying precious extra milliseconds for computations that would otherwise fail. Beyond computing, the effect could rewrite chemistry. Chemical reactions rely on quantum tunneling, where particles bypass energy barriers to form new bonds. But with precise Zeno-like interventions, scientists might one day steer these reactions, freezing them mid-process to isolate unstable intermediates or redirect molecular pathways. Imagine designing catalysts that pause exactly when needed, enabling ultra-efficient fuel synthesis or pharmaceutical production. Experiments with ultra-cold molecules hint at this potential, showing how repeated measurements can suppress unwanted reactions, like a quantum traffic cop halting rogue particles at an intersection. Yet the implications dig deeper than engineering. The Zeno effect blurs the line between observer and participant, suggesting that reality isn't just seen, it's shaped by interaction. Some interpretations even speculate that consciousness could exploit this mechanism, with focused attention influencing quantum outcomes in ways we don't yet grasp. It's a controversial idea, but the underlying principle is undeniable. In the quantum world, to watch is to change, and to measure is to control. So next time you glance at a ticking clock, consider this: the act of looking might be more than passive. It could be the hand that winds the gears or stops them cold. The universe is unfathomably vast, billions of galaxies, each with billions of stars, countless planets spinning in the Goldilocks zones where life could thrive. With odds like that, the cosmos should be teeming with civilizations. So where is everybody? This haunting question, posed by physicist Enrico Fermi in the 1950s, has gnawed at scientists for decades. But what if the answer lies not in the vastness of space, but in the quantum weirdness simmering beneath reality's surface? Could the very fabric of quantum mechanics hide or even erase advanced civilizations from our view? Consider the eerie silence first. Despite decades of scanning the skies with radio telescopes, we've found no definitive signals, no megastructures blotting out stars, no cosmic engineering projects lighting up the darkness. Traditional explanations range from the grim, maybe intelligent life self-destructs before reaching the stars, to the pragmatic, perhaps spacefaring cultures are just too far apart in time or distance. But quantum mechanics offers a stranger possibility. What if advanced civilizations don't interact with the universe in ways we can detect because they've learned to harness or become entangled with quantum processes? Here's where quantum biology whispers tantalizing clues. We already know nature exploits quantum tricks in unexpected places. Photosynthesis in plants relies on quantum coherence to funnel energy with near-perfect efficiency. Migratory birds navigate using entanglement in cryptochrome proteins, their internal compasses sensitive to Earth's magnetic field. If life on Earth stumbled onto these quantum shortcuts, why wouldn't intelligence elsewhere master them on a grander scale? An advanced civilization might engineer entire ecosystems or even their own biology to operate in quantum superposition, existing in multiple states or locations simultaneously. To outside observers, they'd flicker in and out of detectability like particles in a double-slit experiment. They're one moment, gone the next, or perhaps they've transcended classical communication altogether. Imagine a species that encodes information not in radio waves but in quantum-entangled networks, transmitting thoughts or data instantaneously across light years. Such signals wouldn't just be invisible to our current technology, they'd be fundamentally uninterceptable. Any attempt to eavesdrop would collapse the entangled states, erasing the message. It's like trying to catch smoke with your hands. The harder you grasp, the less there is to hold. Then there's the darkest quantum twist, observation itself as a cosmic filter. In the many worlds interpretation, every quantum decision spawns branching universes. Could it be that in most branches, civilizations rise and fall without ever developing the tools to reach out, but in the rare slices where they do, their very act of observation alters their detectability? Like a quantum Zeno effect on a galactic scale, the more a civilization peers into the void, the more it locks itself into a timeline where contact is impossible. The universe's quantum rules might enforce a kind of cosmic isolation, a built-in firewall preventing civilizations from ever bridging the gap. None of this is proof, of course, just a mind-bending lens on Fermi's paradox. But it underscores a humbling truth. If quantum mechanics governs not just particles but the fate of intelligence itself, then the silence of the cosmos might not be empty at all. It could be vibrating with civilizations we're blind to, their presence woven into the static of space-time, waiting for us to learn the right way to listen. Until then, the stars keep their secrets not out of malice, but because reality itself might be playing by rules we're only beginning to guess. Plants don't know quantum mechanics, but they use it better than most scientists. Take photosynthesis, nature's ultimate solar panel. When sunlight hits a leaf, its energy needs to travel through a maze of molecules to reach the reaction center where photosynthesis happens. Classically, this journey should be inefficient, like a blindfolded explorer stumbling through a forest. Yet plants achieve near-perfect energy transfer, and quantum coherence might be their secret weapon. Experiments show that light-harvesting proteins in green sulfur bacteria exploit quantum superposition, allowing energy to test multiple pathways simultaneously and instantly choose the most efficient route. It's as if the leaf performs trillions of calculations per second without a single synapse, leveraging quantum weirdness to turn sunlight into survival. Birds navigate continents with similar quantum mastery. The European robin migrates thousands of miles with pinpoint accuracy, guided not just by stars or landmarks but by Earth's magnetic field. Hidden in their eyes lie cryptochrome proteins, where light-triggered quantum entanglement creates a compass more sensitive than any human-made device. When a photon hits cryptochrome, it knocks an electron loose, creating a radical pair, two entangled electrons whose spins respond to magnetic fields. The bird perceives these quantum states as visual cues, painting the planet's magnetic contours across its vision like an augmented reality overlay. Break the entanglement and the navigational magic vanishes. Evolution, it seems, cracked quantum sensing long before physicists even knew it existed. Even human smell might whisper quantum secrets. Traditional lock and key theories suggest odor receptors identify molecules by their shape alone. But some compounds with identical shapes smell completely different, while others with wildly different structures share nearly identical scents. Quantum tunneling could explain this. As odor molecules vibrate, electrons might tunnel through them, with receptors detecting these quantum vibrations like a molecular piano striking distinct notes. Experiments with deuterium substituted molecules chemically identical but heavier. Altering vibration frequencies show humans and fruit flies distinguish them by scent alone, hinting at a quantum layer to our most primal sense. These aren't isolated quirks. Enzymes, the workhorses of biochemistry, may exploit quantum tunneling to accelerate reactions millions of times faster than classical chemistry allows. DNA replication, long assumed to follow Newton's predictable rules, might rely on proton tunneling to avoid mutations. A quantum proofreading system evolved over eons. Even the human brain's microtubules have been theorized, though hotly debated, to harbor quantum vibrations influencing consciousness itself, a controversial idea called orchestrated objective reduction. The implications are staggering. If biology routinely harnesses quantum effects, it suggests nature evolved to exploit the universe's hidden rules long before we articulated them. Synthetic biologists now race to mimic these tricks, designing quantum-enhanced solar cells inspired by leaves or ultra-sensitive magnetic sensors modeled on avian navigation. Meanwhile, quantum physicists scour living systems for clues to stabilize coherence in warm, wet environments, something labs struggle to replicate outside cryogenic freezers. Yet mysteries abound. How do biological systems maintain coherence despite constant molecular noise? Is quantum biology a happy accident or an inevitable optimization forged by evolution? And if life is steeped in quantum mechanics, might consciousness itself emerge from processes we've yet to fathom? The answers could rewrite not just biology, but our place in a universe where the line between life and quantum physics blurs into irrelevance. One thing's certain, the more we look, the more we find nature didn't just adapt to the quantum world, it became fluent in it. What if everything you know, the stars, your memories, even the sensation of breathing, is just data in some unfathomable cosmic computer. The simulation hypothesis, once relegated to science fiction, has gained startling traction among physicists and philosophers, with quantum mechanics handing it unexpected credibility. At the heart of this radical idea lies a simple observation. Our universe behaves suspiciously like an ultra-high-resolution video game with quantum mechanics acting as the source code. Start with the pixelation of reality itself. Quantum theory reveals that energy, momentum, and even space-time aren't continuous but come in discrete chunks, tiny, indivisible units called quanta. This isn't just theoretical. Planck's constant, the fundamental number governing these quantum steps, sets a minimum resolution for the universe, much like how a digital image breaks down into individual pixels when you zoom in far enough. Even time may not flow smoothly but advance in tick-tocks of Planck time intervals so short, 10 to the power of negative 43 seconds, that they're the universe's equivalent of a processor's clock cycle. If reality were a simulation, these quantum limits would perfectly explain why we can't detect anything finer. We're bumping up against the program's rendering limits. Then there's the observer effect, quantum mechanics' insistence that particles don't settle into definite states until measured. In a simulation, this makes eerie sense. Why waste computing resources rendering every particle in every possible state? Only when a player, or in this case, a conscious observer, looks does the system need to generate an outcome. It's a cosmic version of video game level of detail optimization, where distant terrain stays blurry until a player approaches. The double-slit experiment, where particles behave as waves until observed, mirrors this perfectly. The simulation only bothers calculating the wave function when no one's looking, then snaps to a single result when forced to display it. Even quantum entanglement fits the simulation narrative. Instantaneous correlations between particles, no matter how far apart, defy classical physics but align neatly with how a program might handle linked variables. If two objects in a game share a reference code, changing one automatically updates the other, no speed of light delay required. This would explain why entangled particles communicate faster than light. In the simulation's code, they're not separate entities but two expressions of the same underlying data point. But is this more than a sci-fi metaphor? Philosopher Nick Bostrom formalized the argument in 2003. If advanced civilizations eventually run ancestor simulations, hyper-realistic reconstructions of their past, the number of simulated minds would dwarf biological ones. Statistically, we're more likely to be among the simulated. Tech moguls like Elon Musk have echoed this, citing video games' exponential progress as proof that photorealistic simulations are inevitable. Critics, however, see glaring flaws. If the universe is a simulation, where's the glitch? Where's the evidence of computational shortcuts or rounding errors? Some suggest high-energy cosmic rays could be the equivalent of buffer overflows, rare moments when the simulation strains under complexity. Others point to quantum randomness as the noise of underlying calculations. But these are speculative at best. Moreover, the hypothesis is unfalsifiable by design. Any anomaly we discover could just be part of the simulation's rules. The debate straddles science and philosophy. If true, the simulation hypothesis redefines existence, turning physics into reverse engineering someone else's programming. If false, it's still a provocative lens on quantum oddities, why our universe seems so finely tuned, so computational. Whether we're living in a cosmic matrix or not, one thing's clear: quantum mechanics has already shown us that reality is far stranger than it appears. The question isn't just whether we're in a simulation, but whether we'd ever know the difference. Every time you make a choice whether to turn left or right, speak or stay silent, quantum mechanics suggests another version of you takes the road untraveled. This isn't poetic metaphor. The many worlds interpretation insists that every quantum decision spawns a branching tree of realities. each a complete universe with its own timeline and consequences. But this isn't the only multiverse theory vying for legitimacy. Cosmologists studying the aftermath of the Big Bang propose a wildly different kind of parallel existence, one where infinite bubble universes float in an ever-expanding cosmic foam, each with its own unique laws of physics. Both ideas invoke countless alternate realities, yet they emerge from entirely distinct corners of science, painting startlingly different pictures of what infinity truly means. Start with the quantum version. In the many worlds framework, there's no wave function collapse, just ceaseless splitting. When an electron passes through a detector, its wave function doesn't resolve into a single position. Instead, reality divides, one universe where the electron lands here, another where it lands there. Extend this to human decisions and the implications are dizzying. A version of you exists where every quantum coin flip, every career move, every chance encounter unfolded differently. Unlike science fiction's trope of hopping between dimensions, these branches are forever severed, diverging at light speed. Yet they're equally real, woven into the quantum fabric like threads in an endless tapestry. Now contrast this with inflationary cosmology's multiverse. According to leading theories, the Big Bang wasn't a one-time explosion but the local eruption of an eternally inflating space-time. Picture a boiling pot of water, where each bubble represents a self-contained universe with its own physics. Some bubbles might have stronger gravity, rendering stars impossible. Others could harbor dimensions beyond our three, or dark energy densities so high that matter never coalesces. Crucially, these universes aren't linked by quantum branching but are born separate from inception, floating in a meta-universe where the very concept of distance loses meaning. The evidence, it's subtle but mounting. Measurements of the cosmic microwave background, the afterglow of the Big Bang, reveal anomalies that some theorists argue are bruises from collisions with other bubble universes. Meanwhile, string theory posits a landscape of possible universes, each corresponding to different configurations of curled-up extra dimensions. If true, our universe's finely tuned constants, the precise strength of gravity, the mass of the electron aren't miracles but inevitabilities. With infinite bubbles, some had to hit the jackpot for life, yet the two multiverses couldn't be more different in origin. Many worlds emerges from quantum determinism. Every possibility must happen. Inflationary bubbles arise from random fluctuations in an energy field. One generates branches through observation, the other spawns disconnected realms through runaway physics. Both challenge anthropocentrism, hinting that we're neither special nor alone, just statistically likely in a sea of improbability. But here's the twist that ties them together. If the many worlds interpretation is correct within our inflationary bubble, then the multiverses multiply fractally, infinite branches within infinite bubbles. A humbling thought, somewhere in some layer of reality, there's a universe where none of this is speculative. They've already mapped the totality of existence, while another version of them is still scratching their heads just like us. What if your thoughts aren't just the firing of neurons, but the hum of quantum vibrations reverberating through the fabric of reality itself? This bold idea lies at the heart of quantum consciousness theories, where the boundary between mind and quantum mechanics blurs into something extraordinary. At the forefront is physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, whose orchestrated objective reduction theory proposes that consciousness isn't merely a computational byproduct of the brain. It's a quantum phenomenon unfolding in the tiny tubular structures inside your neurons called microtubules. Microtubules are the scaffolding of cells, hollow polymers that maintain structure and transport materials. But Penrose and Hameroff see them as something far grander, quantum processors. Their theory suggests that within these nanoscale tubes, electrons dance in superposition, their quantum states resonating until reaching a threshold where gravity, yes, gravity forces them to collapse. Each collapse is a moment of conscious experience, a fleeting now in the stream of awareness. It's as if your brain isn't just computing thoughts but conducting a symphony of quantum collapses, with each note a flicker of subjective experience. The implications are staggering. If true, this would mean consciousness isn't confined to classical physics but is deeply rooted in the quantum world, perhaps even explaining why we experience a unified sense of self rather than a chaotic jumble of neural signals. It might also bridge the infamous hard problem of consciousness, why and how physical processes give rise to inner experience. In this view, qualia, the raw feels of redness, sweetness, or pain aren't emergent illusions but fundamental quantum events. Critics, however, pounce on two major hurdles. First, the brain is warm, wet, and noisy, a seemingly hostile environment for delicate quantum states. Decoherence, the bane of quantum computing, should obliterate any superposition in nanoseconds. Yet Penrose and Hameroff counter that microtubules might be shielded by ordered water molecules or nonlinear resonances, creating pockets where quantum coherence survives long enough to matter. Second, there's scant experimental evidence. While studies show microtubules can exhibit quantum-like vibrations, no one's yet caught them in the act of sustaining superposition. Recent research teases tantalizing possibilities. Experiments with anesthetics chemicals that selectively switch off consciousness reveal they bind to microtubules, disrupting their quantum oscillations. Conversely, psychedelics like DMT appear to enhance these vibrations, correlating with altered states of awareness. Meanwhile, lab-grown mini-brains, organoids, could soon let scientists probe microtubule dynamics in near real time, searching for quantum signatures amid the neural chatter. The debate rages on. Some theorists propose alternative quantum consciousness models, like psychiatrist Ian Marshall's hypothesis that the brain's electromagnetic field integrates quantum information. Others dismiss the idea entirely, arguing classical neural networks suffice to explain awareness. Even if microtubules aren't quantum mind hubs, their structure might still inspire radical new computing architectures, blurring the line between biology and quantum technology. So where does this leave us? Quantum consciousness remains a fringe but electrifying frontier where the mysteries of mind and matter collide. Whether it's validated or debunked, the very pursuit forces us to confront a profound question. Could the universe's deepest enigmas, from entanglement to observation, somehow be woven into the fabric of our own awareness? The answer, whatever it is, might redefine not just what we are, but what reality itself is capable of. Of all the numbers that shape our universe, none is quite as baffling as the fine structure constant. Represented by the symbol alpha, this seemingly innocuous value, approximately 1/137, holds the reins of electromagnetism's strength, dictating how tightly electrons cling to atoms, how light interacts with matter, even the very stability of molecules. Tweak it by a fraction and the cosmos as we know it unravels. Make it slightly larger and stars burn too fiercely to last long enough for life to emerge. Nudge it smaller and chemical bonds weaken, turning water into a fleeting impossibility. It's as if the universe dialed this number with impossible precision, not just for life as we know it, but for any conceivable life at all. This razor's edge perfection fuels one of physics' fiercest debates, the anthropic principle. Is alpha fine-tuned because we're here to observe it, or is there a deeper, undiscovered law locking it into place? The first camp argues that in a multiverse teeming with universes sporting random constants, we naturally find ourselves in the rare slice where alpha permits conscious observers. The alternative, alpha isn't arbitrary, it's the inevitable outcome of a grand unified theory we haven't cracked yet. Either answer reshapes our understanding of reality. The mystery deepens when you peer into the cosmos. In 2020, astronomers analyzing light from distant quasars reported potential variations in alpha across space and time, as if the constant isn't so constant after all. If verified, this would upend modern physics, suggesting the laws of nature evolve over cosmic epochs. But these findings remain contentious, with other teams failing to replicate the anomalies. What's undeniable is alpha's fingerprint everywhere, in the spectral lines of stars, the glow of neon signs, even the chemistry of your own DNA. The hunt for alpha's origin spans extremes. String theory posits it's tied to the geometry of hidden dimensions, while quantum field theorists chase elusive action particles that might stabilize it. Meanwhile, lab experiments with ultra-precise atomic clocks test whether alpha drifts imperceptibly over time. The stakes couldn't be higher. Crack alpha's code, and you might unlock why the universe allows atoms, and thus us, to exist at all. Until then, this dimensionless number stands as both a master key and a locked door, guarding secrets that could rewrite the story of everything. Imagine firing photons through a maze where the very act of erasing their history bends reality backward, forcing particles to change their past behavior on a whim. This is the quantum eraser experiment, a demonstration so unsettling that it seems to shred the classical notion of cause and effect. At its core, this experiment reveals something extraordinary. Information, or the lack of it, can rewrite the rules of the universe retroactively, as if time itself is a canvas that quantum mechanics can redraw at will. Start with the classic double-slit setup, where particles like electrons or photons produce an interference pattern when their paths aren't observed. The moment you measure which slit they pass through, that pattern vanishes. The particles behave like simple bullets, not waves, but the quantum eraser takes this further. Scientists add a twist. They mark which path each particle takes using entangled, labeled photons. Then, after the particle has already hit the detector, they choose whether to erase that path information. Astonishingly, when the labels are scrambled, the interference pattern magically reappears, as if the particle retroactively decides whether it traveled through one slit or both, depending on whether its history is later made unknowable. It's as if the universe allows particles to revise their past based on future choices, a cosmic game of oops, never mind. The delayed choice quantum eraser cranks the weirdness to 11. In this version, the decision to erase or keep the path information is made after the particle has already been detected. One experiment sent entangled photons on a journey where their partners were measured much later. When the results were tallied, the data showed that the first photon's behavior, whether it acted like a particle or a wave, depended on how its entangled twin was treated after the fact. This isn't just defying intuition, it's outright inverting it. The present seems to reach backward in time, whispering to the past how it should unfold. What does this mean for causality? The implications are dizzying. Some interpretations suggest that quantum events don't solidify into history until all possible information about them is accounted for, even if that accounting happens later. Others propose that time, at the quantum level, isn't a rigid arrow but a fluid network where future and past negotiate outcomes. There's even a radical idea that consciousness itself might play a role, with observers collapsing reality in ways that ripple backward. Yet beyond philosophy, the quantum eraser has real-world teeth. Quantum cryptography exploits these effects to create unhackable communication. Any eavesdropper trying to peek at quantum data unavoidably leaves marks, alerting users to tampering. And in labs, eraser techniques are refining quantum computers, where controlling information flow could mean the difference between noise and precision. The experiment forces us to confront a humbling truth. Reality might not be a fixed tapestry but a draft, endlessly editable until the last possible moment. Particles don't just exist in superposition, they seem to negotiate their existence across time, leaving us to wonder whether the past is ever truly settled, or if it's just waiting for the future to weigh in. Picture an electron gliding through a region of space where both electric and magnetic fields read zero. No forces pushing or pulling it, just empty stillness. According to classical physics, that electron should sail through unaffected, like a ship on a windless sea, but the quantum world laughs at such expectations. In 1959, physicists Yakir Aharonov and David Bohm predicted something extraordinary. Even in these field-free voids, electromagnetic potentials, the underlying mathematical scaffolding of electric and magnetic fields, can still bend the electron's path, leaving ghostly fingerprints on its behavior. This is the Aharonov-Bohm effect, a phenomenon so counterintuitive that even Einstein found it troubling. Here's how it works. Ordinarily, we think of fields as the real actors. Electric fields jolt charges, magnetic fields deflect currents. But in quantum mechanics, it's the potentials, abstract quantities like the vector potential A and scalar potential letter 3d5, that take center stage. Aharonov and Bohm showed that if you confine a magnetic field inside an infinitely long, hollow cylinder, a solenoid, the region outside the cylinder has zero magnetic field, yet the vector potential there isn't zero. When electrons loop around this shielded field, their quantum waves pick up a phase shift, altering interference patterns in ways that defy classical logic. It's as if the electrons feel the potential's presence even though no force touches them. The experiment confirming this was a masterpiece of precision. Scientists sent electron beams around opposite sides of a tiny solenoid, then recombined them to create an interference pattern. Despite the solenoid's magnetic field being locked inside, the pattern shifted predictably as the field strength changed, proof that potentials, not fields, were pulling the strings. This wasn't just academic sleight of hand. The effect revealed that electromagnetism's true essence lies deeper than forces. It's encoded in the geometry of potentials, with quantum particles acting as ultrasensitive probes of this hidden landscape. The implications ripple across physics. For starters, the Aharonov-Bohm effect cemented gauge theory as the lingua franca of fundamental forces. Gauge transformations, redefinitions of potentials that leave fields unchanged, aren't just mathematical quirks. They're woven into quantum mechanics fabric, with the Aharonov-Bohm phase serving as a gauge invariant signature. This insight paved the way for modern theories like quantum electrodynamics and the Standard Model, where potentials aren't just tools but the very thread stitching reality together. But the weirdness doesn't stop there. The effect also underlies geometric phases in quantum systems, where particles retain memory of their journey's shape even when no forces act. This isn't limited to electromagnetism. Similar phases appear in optics, condensed matter, and even gravitational analogues. Imagine a quantum computer where information is encoded not in fragile charge states but in robust geometric phases immune to noise. Or consider topological materials where edge states conduct electricity flawlessly thanks to Aharonov-Bohm-like protection. Critics once dismissed the effect as a mathematical artifact, arguing that only measurable fields should matter. Yet decades of experiments, from nanoscale rings to superconducting circuits, have silenced doubters. The universe, it seems, keeps its ledgers in potentials, not forces. For electrons, the path not taken isn't just a poetic notion. It's a tangible twist in the quantum tapestry, etched by invisible hands. And that's the true magic of the Aharonov-Bohm effect. It whispers that reality's deepest layers aren't what we perceive, but what we're only beginning to decode. What if the world around us feels solid and stable, not because quantum weirdness disappears, but because the universe itself is constantly voting on what stays and what fades away? This is the radical premise of quantum Darwinism, a theory proposing that classical reality isn't the default state of nature, but the winner of a relentless quantum selection process. Unlike Schrödinger's cat, suspended between life and death until observed, quantum Darwinism suggests that certain quantum states survive and proliferate precisely because they're constantly measured, not by human observers but by the environment itself. Picture a lone electron in superposition, its wave function spreading across multiple positions. The moment it interacts with even a single photon or air molecule, that interaction records information about its state like a cosmic fingerprint. Now scale this up. Countless particles bombard the electron from all directions, each tiny collision reinforcing some states while erasing others. Over time, only the most robust, frequently observed states persist, while fragile superpositions crumble under environmental scrutiny. It's survival of the fittest, but for quantum possibilities, the versions of reality that get copied and shared most widely become the ones we perceive as objective. This is why we don't see chairs in quantum limbo. Their stable positions have been amplified by trillions of environmental interactions, drowning out alternatives. Quantum Darwinism doesn't just explain why the macroscopic world looks classical, it redefines what observation even means. In the traditional Copenhagen interpretation, measurement requires a conscious observer or a classical device. But quantum Darwinism argues that any interaction capable of proliferating information, a photon bouncing off an atom, a dust grain jostling in air, counts as observation. The universe isn't waiting for humans to look, it's conducting a ceaseless poll with the environment tallying votes on what's real. Experimental evidence is mounting. In 2019, a team at the University of California, Berkeley, used nitrogen vacancy centers in diamonds to track how quantum states decohere when bombarded by environmental noise. They found that preferred states, those resilient to disruption, spread their information outward in predictable patterns, like ripples in a pond. Meanwhile, competing theories like decoherence theory align closely with quantum Darwinism, showing how entanglement with the environment naturally suppresses quantum weirdness. Even the famous double-slit experiment gets a fresh twist when which path information is imprinted on the environment, say by scattered photons. Interference vanishes not because of human curiosity, but because the universe has already chosen. But the implications stretch beyond physics labs. If reality emerges from information proliferation, could this explain why we share a common world? Two people looking at a tree both see leaves and bark, not probabilistic smears, because the tree's quantum states have been redundantly broadcast through sunlight, air molecules, and retinal photons. Consciousness might not create reality, it simply taps into the consensus. Some theorists even speculate that quantum Darwinism bridges the gap between quantum mechanics and thermodynamics, with entropy dictating which states spread fastest. Yet mysteries linger. Why do some quantum systems, like high-temperature superconductors, resist classical collapse despite environmental noise? Could artificial environments be engineered to preserve delicate superpositions longer? And if reality is a democratic process, who or what sets the election rules? Quantum Darwinism doesn't just demystify the quantum to classical transition. It turns the cosmos into a self-organizing story where what we call real is simply the version of events that outcompeted the rest. One thing's certain, in this universe, existence isn't a given, it's a privilege earned through countless microscopic interactions, each whispering, "This one." Pay attention to this one. We think we know the proton, a simple, stable speck of matter at the heart of every atom. But what if this familiar particle has been hiding a cosmic secret? In 2010, physicists aimed lasers at exotic hydrogen atoms to measure the proton's radius with unprecedented precision. The results should have matched decades-old data from electron scattering experiments. Instead, they diverged wildly, revealing a proton 4% smaller than anyone expected. This wasn't just a rounding error. It was a full-blown crisis in nuclear physics. Dubbed the proton radius puzzle, this discrepancy suggests either our measurements are fundamentally flawed, or the universe is playing by rules we haven't discovered yet. The plot thickened with muonic hydrogen experiments. When researchers swapped electrons for their heavier cousins, muons, the proton's radius shrank even further, as if the particle itself were adjusting its size based on who was looking. Muons orbit 200 times closer to the proton than electrons, amplifying subtle quantum effects. If the proton's charge cloud behaves differently under this intense scrutiny, it could hint at forces or particles beyond the standard model. Perhaps a yet undetected dark photon, mediating unknown interactions between quarks and leptons. Some theorists reach for even wilder explanations. Could extraspatial dimensions, curled up at fantastically small scales, be warping the proton's apparent size when probed by different particles? String theory predicts such dimensions, but they've eluded direct detection. Alternatively, the puzzle might expose gaps in quantum electrodynamics (QED, the theory governing light-matter interactions. If QED needs correction at extreme proximity, it would send shockwaves through physics, forcing revisions to everything from atomic clocks to quantum computing. The implications cascade beyond academia. Precise proton measurements underpin technologies like positron emission tomography, PET scans, and proton therapy for cancer. If our foundational constants are in flux, these applications might require recalibration. Meanwhile, labs worldwide are racing to resolve the puzzle, from high-precision spectroscopy of helium ions to novel scattering experiments at facilities like CERN and Jefferson Lab. What makes this mystery so electrifying isn't just the potential for new physics, it's the humbling reminder that even the most familiar corners of reality can still surprise us. The proton, a particle we've studied for over a century, might be whispering secrets about dimensions, forces, or particles we've never dreamed of. Until we crack its code, every measurement feels like peeling back another layer of the universe's deepest riddles. Imagine a cat whose grin lingers in the air long after the cat itself has vanished, an eerie image straight from Alice in Wonderland. Now replace the cat with a quantum particle, and you've got the quantum Cheshire cat effect, a phenomenon where a particle's properties, like spin or polarization, seem to detach from its physical location, leaving behind a ghostly imprint of itself. This isn't science fiction. In 2013, a team of physicists designed an experiment to split a neutron's magnetic moment, think of it as its grin, from its actual position, proving that in the quantum realm, a particle's identity isn't just ambiguous, it's divisible. The experiment worked like a quantum magic trick. Neutrons were sent through an interferometer, a device that splits and recombines particle paths. By carefully manipulating magnetic fields, the researchers effectively separated the neutron's magnetic moment from its physical path, detecting the neutron's spin in one arm of the interferometer while its position was recorded in the other. It's as if you walked through a doorway and your shadow stepped through a different one entirely. The implications are staggering. Quantum properties aren't just tied to particles, they can wander off on their own, like a smile without a face. But how is this possible? One interpretation leans on the idea of weak measurement, a technique that gently probes quantum systems without fully collapsing their wave functions. Unlike traditional measurements that force particles into definite states, weak measurements allow scientists to glimpse the average behavior of a property over many trials, revealing where a particle's spin spends time, even if the particle itself isn't there. This isn't just academic sleight of hand. The quantum Cheshire cat effect challenges the very notion of what an object is. If a particle's properties can exist independently, does that mean reality is less like a collection of things and more like a bundle of loosely connected traits? Philosophically, this opens a Pandora's box. If properties can disembody, what does that say about the nature of existence? Some theorists argue it supports a relational view of reality, where particles aren't solid entities but nodes in a web of interactions. Others see it as evidence for pilot wave theory, where particles are guided by hidden quantum fields, their properties rippling ahead like shadows. And then there's the many worlds angle. Could the grin represent a property leaking into a parallel universe while the particle stays behind in ours? The Cheshire cat effect isn't just a curiosity, it's a tool. Quantum biologists speculate that similar separation might occur in photosynthesis, where energy travels without the usual molecular baggage. Quantum engineers, meanwhile, are exploring property-only communication, where information could be transmitted using disembodied spins or charges, potentially evading noise in quantum computers. Even cosmology gets a twist. If particles can shed their properties, could dark matter be an accumulation of quantum grains without particles to wear them? Yet the mystery lingers. Where do we draw the line between a particle and its traits? The quantum Cheshire cat doesn't just grin, it taunts us with questions about the fabric of reality itself. And as experiments push further, probing whether multiple properties can separate at once or even if entire atoms can pull off the trick, one thing's clear. In the quantum wonderland, the rules are written by a narrator we're only beginning to understand. Space isn't just the backdrop of the universe, it might be the universe's greatest illusion. What if the vast emptiness between stars, the very fabric we call space-time, isn't fundamental at all, but something that emerges from a deeper quantum layer, like a 3D hologram projected from a hidden 2D code? This radical idea isn't science fiction. It's the heart of modern quantum gravity research, where physicists are piecing together a theory that space-time itself is stitched into existence by quantum entanglement, the same spooky connection that links particles across galaxies. Let's start with entanglement, that eerie quantum bond where particles share states instantaneously, no matter how far apart they drift. At first glance, this seems unrelated to gravity or geometry. But dig deeper and a stunning pattern emerges. The more entangled two regions of a quantum system are, the closer they behave in space-time. It's as if entanglement doesn't just correlate particles, it generates the space between them. Picture two friends telepathically linked. The strength of their connection doesn't depend on physical distance because, in a sense, the connection defines the distance. This insight crystallized with the AD/CFT correspondence, a groundbreaking conjecture from string theory. It proposes that a higher dimensional spacetime, like our universe with gravity, can be perfectly described by a lower dimensional quantum theory living on its boundary, no gravity required. Think of it like a video game where all the action happens on a flat screen, but the characters experience a fully immersive 3D world. In this duality, entanglement entropy in the boundary theory maps directly to geometric distances in the bulk spacetime. More entanglement means shorter paths, less entanglement creates cosmic gulfs. Suddenly, the fabric of reality looks less like a stage and more like a network of quantum relationships. Lab experiments are catching up to these mind-bending theories. In 2017, researchers at the University of Maryland simulated a toy universe using entangled qubits, showing how space-time geometry could arise from quantum links. Meanwhile, quantum computers are testing holographic principles by encoding information in ways that mimic AD/CFT's predictions. Even black holes fit the puzzle. Their event horizons seem to store information in a 2D form, with the interior volume emerging from the entanglement of surface particles, a cosmic version of the hologram metaphor. But here's the twist that bends intuition further. If spacetime is built from entanglement, then wormholes, those sci-fi shortcuts across the cosmos, might just be quantum entanglement in disguise. Einstein called entanglement spooky action at a distance. Now we're realizing the spookiness is the distance. This could explain why wormholes and entanglement share the same math. Both are threads stitching spacetime together, one from the outside, the other from within. The implications rewrite cosmic history. The Big Bang might not have been an explosion in space, but the moment quantum entanglement patterns crystallized into spacetime itself. Dark energy's accelerating expansion. Perhaps it's the universe's quantum links stretching thin. Even the arrow of time could emerge from entanglement's one-way growth, like a cosmic ratchet turning quantum randomness into the flow we experience. Yet mysteries loom. How exactly do abstract quantum links sculpt the smooth geometry we observe? Are there experimental signatures, tiny quantum gravity fluctuations, hidden in cosmic microwave background data? And if spacetime is a tapestry of entanglement, what happens to reality when we cut those threads? One thing's certain: the closer we look at the void, the less empty it seems. Space isn't just where the universe happens, it's the universe's grandest performance, a magic trick played by quantum mechanics on a cosmic scale. After 30 quantum mysteries, from particles that rewrite their own pasts to black holes that might hide parallel universes, one question looms larger than all the rest. Are we on the brink of a grand unified theory that ties everything together, or is the universe fundamentally unknowable? This isn't just about filling in gaps, it's about whether those gaps are cracks in reality itself. On one side stand the optimists, the torchbearers of Einstein's dream. They argue that every past scientific revolution, Newton's laws, Maxwell's electromagnetism, even quantum mechanics itself, started as a tangle of paradoxes before yielding to deeper understanding. To them, today's mysteries are simply tomorrow's homework. String theory, loop quantum gravity, and other frameworks are works in progress, not dead ends. After all, the Higgs boson was predicted decades before its discovery at CERN. Why wouldn't quantum gravity or dark matter particles hide just beyond our current reach? Their faith rests on history's pattern. Every time we've hit a wall, we've tunneled through, but the pessimists, or perhaps the realists, see a darker possibility. What if some truths are forever veiled by cosmic censorship? Take the event horizon of a black hole. By definition, it's a boundary beyond which information is erased from our universe. Or consider quantum uncertainty, which isn't a lack of precision in our tools, but a fundamental limit baked into reality. Even our brains, evolved to track predators and ripe fruit, might lack the cognitive hardware to grasp dimensions beyond 3 or the true nature of time. Physics, in this view, could be like an ant trying to comprehend the internet, doomed to grasp only shadows. The divide sharpens when you examine specific puzzles. Quantum gravity, for instance, might require energies 1 trillion times beyond our particle colliders to test directly. Dark energy's elusive nature could be hidden in the fine print of spacetime's expansion, forever receding as the universe accelerates away. And if the multiverse is real, with infinite variations of physics, we might never confirm our own universe's rules aren't just a fluke. The optimists counter with ingenuity. Tabletop experiments probing quantum gravity with supercooled atoms, or cosmic microwave background anomalies hinting at other universes. But the skeptics whisper back, what if the universe's deepest answers are like a fish trying to describe water impossible to see from the inside? Yet between these poles lies a third path: radical humility. Maybe the universe isn't unknowable, but it demands we redefine knowing. Classical physics sought certainty, quantum mechanics trades it for probability. Perhaps the next leap won't explain everything but reveal a new language, one where questions like, what is reality, transform into, how does observation shape reality? The mysteries might not vanish, they might simply change form, like ice melting into water. For now, the only certainty is this: whether these 30 quantum mysteries mark the edge of human understanding or the birth pangs of a new physics, they've already reshaped our place in the cosmos. We're no longer just observers of the universe, we're participants, our questions woven into the fabric of the answers, and that in itself is a kind of revelation. The end of quantum mysteries, more likely, it's just the beginning of the next chapter, one where the universe's secrets are stranger than we've dared to imagine. From particles that exist in 2 places at once to black holes that might hide parallel universes, these 30 quantum mysteries don't just challenge our understanding, they shatter it. Each one peels back another layer of reality, revealing a cosmos far stranger, more dynamic, and more interconnected than we ever imagined. Wave-particle duality forces us to rethink what matter truly is. Entanglement defies space and time, binding particles across galaxies with invisible threads. The measurement problem suggests reality itself might be participatory, shaped by observation. And the holographic principle whispers that everything we see could be a projection from the edges of the universe. Quantum tunneling powers stars yet threatens the stability of our electronics. The Casimir effect proves empty space isn't empty at all. It crackles with energy we can't yet harness. The proton radius puzzle hints at undiscovered forces or hidden dimensions. And quantum biology blurs the line between life and the quantum realm, suggesting nature mastered these rules billions of years before we even noticed. Even time itself, that steady arrow we take for granted, might be an illusion emerging from quantum chaos. But here's the real magic: these mysteries aren't isolated. They're threads in a grand tapestry, each one tugging at the others. The uncertainty principle connects to black hole thermodynamics. Quantum Darwinism ties to the simulation hypothesis. Dark matter's enigma might be linked to vacuum energy's paradox. Together, they paint a picture of a universe that's less a machine and more a living, evolving symphony, one where the notes are still being written. So where does this leave us? Not with answers, but with something far more valuable, better questions. The quantum frontier isn't just about solving puzzles, it's about learning to think in ways we haven't yet invented. Maybe the ultimate revelation isn't a theory of everything, but the realization that the universe refuses to be boxed in by our intuition. As the screen fades and you sit with these ideas, here's a challenge. Which mystery haunts you the most? Is it the eerie dance of entanglement, the phantom pull of the Casimir effect, or the chilling possibility of quantum immortality? Whatever it is, let it linger, stay restless, stay curious, because the next great breakthrough won't come from those who fear the unknown, but from those who chase it into the dark. The universe has spent billions of years hiding its secrets. Are you ready to help uncover them?